Okay, we are moving on into chapter 3. Exponential and logarithmic functions. These functions are in the same chapter simply because they are inverses of each other. The exponential function is the inverse of log. Log is the inverse of exponential. Here we're only going to look for, at sections 3.1 through 3.3, nothing else. Exponential functions 3.1. From algebra, we know that exponential functions look like this, where a is the base, and the base can have two options. Can be a number, positive number between 0 and 1, not 0, not 1, or a number strictly greater than 1. Of course, we are looking at two other functions, specific functions. This is the natural exponential function, and f of x, 10 to the x, and which is the common exponential function. I'm hoping that you went through the chapter, you read the sections, you solved the examples that are presented here, and you now remember that when we differentiate the exponential function, when we differentiate e to the x, we get e to the x. When we differentiate e to a function of x, we get e to u times u prime. And you see these definitions on page 313 and also page 315. And I would like to move on to some examples. Let's look at problem 25 on page 319. We are given a function f of x, which is negative 2/3 e to x squared, which is this particular situation where x squared is u. This is x squared. So when we find the derivative of this function, f prime of x, we have negative 2/3 e to u prime is e to u times u prime. U prime is 2x. I'm going to rearrange this expression and write negative 4x divided by 3 e to x squared. Let's look also problem 45 on page 319, where we have y equals the square root of e to the x minus 1. Well, we know how to differentiate this. The square root of a function prime is 1/2 the square root of the function times the function prime. So y prime or dy over dx, same thing, is 1/2 the square root of e to the x minus 1 times the inner function prime, which is e to the x. I'm going to just rearrange and write e to the x over 2 the square root of e to the x minus 1. Problem 63 on the same page. We're asked to graph this function g of x equals 2, 1 minus e to negative x. And we are given the domain of this function 0 to infinity. We're going to go through everything, all the steps that we normally go through when we graph a function. So first of all, I'm going to look at the derivative of this function, but not before I show a couple of presentations for this function. Here's one. 2 and 1 minus 1 over e to the x, which is the same with 2. Find the least common denominator, e to the x. So e to the x minus 1 over e to the x. So when I differentiate this function, however, I prefer to write the function, which is this, same thing, same function, as 2 minus 2 e to negative x. this is what I'm going to differentiate. It's easier than this, it's easier than that. So when I differentiate G prime and get G prime, 2 prime is 0, minus 2. E to U prime is E to U times U prime. So this is nothing else but 2 to E over E to the X. Now when I differentiate, of course, this is nothing else but 2e to negative x. When I differentiate again, I'll get g's second derivative of g, which is this prime, which is 2e to negative x times negative x prime, which is negative 1. So this will be 2 over e to the x. Now, g of 0, go back. E to 0 is 1. 1 times negative 2 is negative 2. 2 minus 2 is 0. And also I need to determine the limit as x approaches infinity from 2 minus 2 over e to the x. As x approaches infinity, this quantity will approach infinity. However, 2 over infinity will approach 0. So the limit is 2. Therefore, y equals 2 is a horizontal asymptote at infinity only. I'm ready to create my chart. So this is g prime, this is g of x, and this is the second derivative, 0 to infinity. G of 0 is 0. The limit at infinity is 2. So y equals 2 is a horizontal asymptote. I'm looking at the first derivative. This is a quantity that is always greater than 0 and never 0, of course. 2 over e to the x is never 0. Same thing here, always less than 0 and never equal to 0. So positive and negative. From 0 to 2, the function is increasing, and this is shown by the sign of the first derivative. So let's graph this function then. Nothing on this side. G of 0 is 0 and equals, and this is y equals 2, the horizontal asymptote. And always opening up, opening down, and always increasing from 0 to 2. And this is the graph of g of x, 2 minus 2e to negative x. Okay, that's my page 3. Okay, find the equation of the line tangent to the graph of problem 77. We have g of x, which is e to negative x, and at the point 0, comma 2. Find the equation of the tangent line. So this is the same page, 319. Find g prime of x, which is negative e to negative x. Evaluate it for x equals 0, which means e to 0 is 1. 1 times negative 1 is negative 1. Y minus y1 equals the slope times x minus x1. The point is given to us as 0, 2, and the slope is negative 1. Therefore, y minus 2 equals negative x minus 0, or y equals negative x plus 2. We move 2 to the other side. And I think we can work on a word problem now. Let's say problem 83 on page 320. It's entitled Marginal Cost. A company's total cost in millions of dollars is given by, so C of t equals 100 minus 50 e to negative t. This is in millions. Where t is time in years. T in years since the startup date. Okay. Find each of the following: the marginal cost, C prime of t. C prime of t equals negative 50 equal e times negative e to negative t times negative 1, so it's 50 e to negative t. C prime of 0 is 50 million per year. It's a rate of change. Like any rate of change, the measurement unit is a ratio of two different measurement units. C prime of 4 C prime of 4, I'll grab my calculator right now, and I have 100, where is it? I'm sorry, 50 times e to negative 4. And this is in millions, so it's roughly, I'm going to write 916 million. So this is per year. That's the rate of change when t is 4 years. Find the limit now. Part D, we're asked to find the limit of c of t when t approaches infinity, and limit of c prime of t as t approaches infinity. Why do you think the company costs tend to level off as time passes? Okay, so let's look at c of t. If as t approaches infinity, so let me write it so we can see it. So this is 100 minus 50 divided by e to t. As t approaches infinity like before, this will approach infinity. However, this will approach 0. So the answer will be, as the limit as t approaches infinity, as time goes by, the limit of c of t as t approaches infinity is 100. Let's look at the limit of c prime of t as t approaches infinity. So that is 50. Limit t approaches infinity, 50 over e to t. Well, this is obviously 0. And now the question is asking us to, why do you think the company costs tend to level off as time passes? And the reason is that this quantity approaches 0 as time passes, so therefore the costs will level off to 100, to the nearest 100,000 in millions of dollars. So 100 million. Anything else here? Maybe one more problem and then we can move on. So 85, same page, 320. At a price of X dollars, the demand in thousands of units for a certain music player is given by the demand function Q, 240 e to negative 0.003 times X. One more time, X in dollars, thousands of units. Thousands of units. Thousands of units. Okay, very good. I don't want to forget that. How many music players will be bought at a price of 250? So part A, as X is 250, we'll plug it in my calculator. So I have 240 multiplied by E raised to 0.003 multiplied by 250. And I get that the price is in thousands. So Q, the number of units, I'm sorry, 113, we're asked to round to the nearest 1,000 units at the price of 250. The demand is this. Part B, graph the demand function for between 0 and 400. So graph the demand function. Oops. And that's my page 4. So very good. So when x is 0, obviously we have 240. Let's see what happens when x is 400. Put in the calculator. 240 multiplied by e raised to negative 0.003 times 400, and I get 72, roughly. Very good. Now I'm looking at the first derivative, q prime, the demand function. So this is negative 240 e to negative 0.003x multiply. I already put the minus in front, 0.003. So I am going to multiply 240 by 0.003, and I get 0.72. I'm not missing anything? No? Okay. 2 zeros, yeah. Very good. So this is negative 0.72 e to negative 0.003x, which is the same thing with this, which is always a quantity that is negative, never zero. Now let's look at the second derivative. It will be, I will differentiate this and multiply 0.72 by 0.003, and I get 0.00216 e to negative 0.003x, which is the same with this, which is always a positive quantity. So between 240 and 72, the function is decreasing, and the sign is supported. That sign supports the decrease. And it opens up. So ready to graph this function. One, two, three, 400. And 1, 2, 3. So this is 240. And at 400 is 72. Function is decreasing and opening up. Here it is. Find the marginal demand Q prime. We already did. That was part C. This is part C. We already found the marginal demand. Interpret the meaning of the derivative. So what does the derivative mean? It's the rate of change. So D. Q prime of x. Rate of change of demand with respect to price per unit x at any point, or price, I would say, x. How fast is changing for any price x. I think we can move on now to 3.2, logarithmic functions. 3.2, logarithmic functions. And this is my page 5. Okay. It starts on page 322. I hope you look at the properties of log. I hope you look at the definition. The definition of a log function is log base b of x, where b has the same properties. It can be either between 0 and 1 or between 1 and infinity. And we have two situations here, which one is L and X, where b is e for this function. And we also have log x, where b, or the base, is 10. And this is the natural log function, and this is the common log function. Okay, I'm going to go directly to the derivative. So the derivative of, so f of x equals natural log x, f prime of x equals 1 over x. And of course, if we have natural log of a function of x, then f prime of x will be 1 over u times u prime. And I'm looking now, I'm on page 334. I'm not going to solve equations, but I'm going to just move on to differentiate different functions. Like, for example, let's say 55. 55 on page 334. So we have g of x, which is x squared times natural log of 7x. G prime of x, as we've noticed already, this is a product function, first function, second function. So I have to differentiate the first function. I get 2x natural log of 7x plus x squared. And I differentiate the second function, 1 divided by 7x, multiplied by 7x prime, which is 7. And yes, I will simplify by 7. And this was multiplied, sorry. So the first function prime, 2x times the second function plus the first function times the second function prime. And I will simplify again. So the simplified form is 2x natural log applied to 7x plus x. Excuse me. So this is the final form. Let's look also at maybe a ratio like 63 on the same page, 334. And f of x equals natural log of x squared minus 7 divided by x. There are several options here, and I could write natural log of x squared minus 7 minus natural log x. This is one of the properties of log. And let me go back so I'll tell you exactly where the properties are found. They are presented in the book on page 325. Properties, page 325. And now I can differentiate, which I get 1 over x squared minus 7 multiplied by the inner function prime, which is 2x, minus 1 over x. And I can leave it as is. And that's the final form. I think we got that idea. And I'd like to move on to word problems, a couple of word problems here with a log function. So I'm on page 6. Let's say advertising 79 on page 334. A model for consumers' response to advertising is given by n of a, which is 2,000 plus 500 natural log a, of course, for a greater than or equal to 1. N of a is the number of units sold. And a is the amount spent on advertising. A in thousands. How many units were sold after spending $1,000 on advertising? So part A, and of, so A is in thousands. So how many units were sold after spending 1,000? So it means A equals 1. And we have 2,000 plus 500 natural log 1. This is 0. 0 times 500 is 0. So 2,000 units. Find f prime of A. Okay, so this is 0. 500 divided by A. And now find Fn prime of 10, which is 10,000. So 500 divided by 10. And we get 50 units. Find the maximum and minimum values if they exist. So we're looking at n prime of a for a being greater than or equal to 1. I doubt that that's the infinity, but n prime of a and n of a. So n prime of a is a function that is always positive. N of 1 we already have is 2,000 units. Now what happens if I want to determine the limit? The limit of n of a as a approaches infinity, right here. So limit of n of a as a approaches infinity. So a approaches infinity, infinity times 500 is infinity, plus 2, so this is infinity as well. So I will have to conclude that this function does not have a maximum, no max, but minimum at a equals 1,000. How much is the minimum? So we already have minimum function value is 2,000 units. Okay, find the limit now of n prime of a. N prime of a, I'm just going to copy it here, is 500 divided by a. We're asked to find the limit as n approaches, as a approaches infinity of, so this is 0. Discuss whether it makes sense to continue to spend more and more dollars on advertising. So the function, the more money we spend on advertising, the function, the number of units sold is increasing. So at infinity, the rate of change of this function is 0. The more money we spend on advertising after a certain amount, as a increases without bound, it will not make any difference. To continue to spend more and more dollars on advertising after a certain amount, it will not make any difference. Okay, last problem here. Let's look at problem 89 on page 335. Walking speed. And we do have a study that gives us the walking speed v in feet per second of a person living in a city of population p population, in thousands, is given v of p, 0.37 natural log p plus 0.05. The population of Seattle is p equals, so part A, p equals 571 in thousands. What is the average walking speed of a person living in Seattle? So v of 571, I will put it in my calculator and I get 0.37 natural log of 571 plus 0.05, and oops, I put negative instead of 0.37, please. Natural log of 571 close plus 0.05, please. And we get that the walking speed is roughly 2.4 feet per second. In part B, let's see, population of New York will be 8100. and we're asked to find the same thing. So I'm just going to insert 8100 and clear the other three. And it appears to be 3.4 approximately. V of 8100 approximately like here as well, 3.4 feet per second. Finally, they want us to find V prime of P. Okay, no problem. That's my page 7. So part C, V prime of P. And that is 0.37, 1 over P, and that's it. 0.37 over P. Interpret V prime of P found in part C. Oh, rate of change of walking speed with respect to the city's population. Okay, I think we can move on to the very last section of this chapter, which is 3.3. 3.3, applications of growth models. 3.3. Applications of growth models. On page 349. $349, $350, $351. Why not? Let's start with 43 on page 350. Limited population growth. A ship carrying 1,000 passengers has the misfortune to be wrecked on a small island from which the passengers are never rescued. The natural resources of the island restrict the growth of the population to a limiting value of 5780, to which the population gets closer and closer, but which it never reaches. The population of the island after time t in years is approximated by the logistic equation. P of t, 5780 over 1 plus 4.78 e to negative 0.4 t. Part A, find the population after 1, 0, 1, 2, 5, 10, and 20 years. Zero, 1, 2, 5, 10, 20. Got graphing calculator in y equals. I will put in the function 5780 divided by 1 plus parentheses, don't forget, 4.78 times e to negative 0.4, close the x, close the parenthesis for the exponent, and then close the parenthesis for the denominator. And go to second and table. And I want 0, 1, 2, 5, 10, and 20. So here's what I got. For 0, 1,000, as we expected. We knew that from the beginning. For 1, 1374. I cannot round out up number of people. 1836. 3509, 5314, and 5770. Okay. Find the rate of change P prime, part B. I am going to replace this function by this function. And now differentiate. P prime of t equals 5780 multiplied by negative 1 multiplied by 1 plus 4.78 e to negative 0.4 t to -2 multiplied by the inner function prime, 4.78. 1 prime is 0. 4.78 times e to -0.4t times the inner function prime, -0.4. So now let's see what I can do to simplify this a little bit. I have two negatives, so that's a positive. Multiply 5780 by this. So 5780 multiplied by 4.78 and multiply by 0.4. 5780, 4.78, okay. 11051.36. Everything over. This goes to the denominator. This goes to the denominator. And this is b prime. Finally, sketch a graph of the function. I'm not going to differentiate this again. I'm only going to plot these numbers, these ordered pairs. So let's do just that. So t is the number of years. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5. So the function goes from 1000 to roughly 5770. I already know that this must be the horizontal asymptote. So this must be y equals 5780 for sure. And now I'm going to plot the points I have. This is one time in which I will not use more calculus. This is definitely a positive number, always. So, and never 0. So the function must be increasing. We'll check in a minute whether we need to find the second derivative. I don't recommend it. There is no need. So let's plot the points. So if this is roughly 6,000, I have 1, 2, 3, 4, 5. 1,000 is here at 0. At 1 is this. At 2 is this. At 3, 1, 2, 3, 5. At 10 and at 20. With the graphing calculator to check, I will put in, oh, I did have it. Okay, 5780, of course I did. Okay, 1 plus 4.78, no problem. -0.4, x, close and close. Okay, so with window, I want x to be between 0 and 20, roughly. It can go further. I want the scale to be, I could use 5. Y minimum 0, but definitely Y maximum, I don't want it more than 6,000 with a scale of 1,000. And I go back to Y equals, and I'm going to put this number, which is 5780. So I have the function, I have the horizontal asymptote. And one more time, the viewing window 0, 30 with a scale of 5, 0 to 6,000 with a scale of 1,000. Here's the graph. As I expected, it appears that it starts with opening up and there is an inflection point and it changes concavity. This is how it seems to me, and according to the points I have. So something like this It never touches the horizontal asymptote. Here's the graph. I think we should look at one more problem here. And I go to page 8. Let's say the spread of a rumor. Okay, let's look at 49. On page 351, the spread of a rumor. We're given in this particular problem, we are asked to fit use regression to fit a logistic equation. So we have n of t to c over 1 plus a e to negative bt and to the data. Estimate the limiting value of the function. At most, how many students will hear the rumor? Okay, so in part A, we're used to use regression. We're asked to use regression to fit a logistic equation. So we're asked to find A, B, and C given the information we have in the table. So let's create a table. We go to second and, no, just stats. And we want to edit. We're going to go to edit. And if you have anything, just clear those. If you have anything in those lists, just clear them. I'm going to create list 1. It's just numbers between 1 and 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And now we're given 1, 2, 4, 7, 12, 18, 24, 26, 28, 28, 29, and 30. So we created those 2 lists. And now in statistics, we go to linear regression. However, we don't have a exponential regression. Logistic. Okay, logistic. Use regression to find the logistic equation. So we press enter. And we are calling list L1, comma, list L2. And press enter. Still working. Finally, thank you. Okay, so it's done. We have C, which is at the top, 79.5676. Their letters are different. So this is, I'm sorry, I just put the wrong one up there. Sorry. So C is 29.47. I don't know how many digits we should keep. It all depends. Does it say? It does not tell us how many digits. I'm going to copy them all then. So here it is. C, 29.47232081. Everything divided by 1 plus A, 79.56767122 times E, finally, to negative 0.809743969 t. Very good. In part B, estimate the limiting value of the function. At most, how many students will hear the rumor? Okay, so this was part A. In part B, limit as t approaches infinity from n of t. So as we know, when t approaches infinity, this quantity will approach negative infinity, and e to negative infinity will approach 0. Therefore, this whole thing will be 0. 0 plus 1 is 1. So this is the limiting size. So this must be 29 students. Is there part C? Graph the function. Okay. Find the rate of change, n prime of t. Okay. Part C. Graph. Zero to infinity. Limiting size. 10, 20, 30, so the horizontal asymptote, y equals 29. And we'll graph it in a moment. In part D, find the rate of change n prime. Okay, rate of change n prime. I would prefer to differentiate this and then plug in the numbers. So I'm gonna change this into C times 1 plus a times e to negative bt raised to negative 1. So C times negative 1 times 1 plus a e to negative bt to negative 2 times the inner function prime. A e to negative bt times negative b. So like before, negative b with the number in front will be bc, and everything divided by a, b, oh, I'm sorry, e to bt from here, and 1 plus a e to negative bt to the second power. So one more time, this is e. It's this quantity that goes to the denominator. This is right here. A e to negative bt becomes a e to bt, and this has negative power, so it goes to the denominator as well. So that is the rate of change of n, which one more time is no, n is the number of students who have heard a rumor, and t is the time in days. Okay, so we found the rate of change. Last question here, and we'll come back to the graph in a moment. We are asked to find the limit of n prime of t as t approaches infinity. Well, as t approaches infinity, this will approach 0 because it's 1 over e, 1 over infinity. So then this whole expression is 1. All this here is 1. And this again becomes e to infinity, which is 0, a number over 0. So this will approach infinity. A number over infinity, and this is 1, will be 0. And explain its meaning. As time goes by, this number of days increases without bound. The rate of change, the limit of the rate of change is 0. Nothing will happen after a certain amount of time. Everybody has heard it. So there is no rate of change. The limit of the rate of change is 0. So now here, in order to graph this function, I see that the derivative is a positive number, never 0. And I know the function will be always increasing. So when t is 0, what happens when t is 0? When t is 0, this is 1. So I'm dividing 29 by 80. So 29 divided by 80 is 0.3625. So when t is 0, the number of students is 0. Now, I should determine the second derivative and see whether the function has an inflection point or not, or you can do that later. I just would like to graph this function with a graphing calculator. Of course, the second function will be 29. That's the horizontal asymptote. And I'm just going to put in 29 divided by 1 plus 80. Let's leave it at 79 times e to negative 0.8x. And I want the viewing window this time to be between 0 and 30 with a scale of 5, that's fine, and 0 to 30 and with a scale of 5. Let's see, where is my graph? 29. Okay, so 29 divided by 1 plus 79 times e. Okay, I should be okay now. Got it. Same, and y equals 29 is coming up. So the graph, like the previous one, opens up, has an inflection point, and then continues to increase at all times, but it has an inflection point. The reason why I didn't find the inflection point is because the calculations were too involving, although it's not going to be difficult to determine the second derivative and find this inflection point. Thank you.